this is going to be a different lecture today. It's going to be nothing like any lecture you've ever seen before, because what I'm going to teach you today is, so when I were a lad, when I were your age, I studied physics, and I took one course randomly. I normally took the M modules, which is like the hard maths modules, but one time I thought, okay, I'm going to take a non-M module because it's third year, and these, no one outside of the world of physics cares that you took the hard modules. All they care about is that you have good grades. So it's like, I'll take the ones where I think I can get a decent grade and they look interesting. So I took one called computational physics, and this is just after I started using Unity and finally like making video games. And this came at the perfect time in my life, this one course, which I think was incredibly useful. I've never seen it taught anywhere else. I've never seen anything like it. About 8 people actually took this course, and I had like the best lecturer ever. It was called Euler-Cromer, and he taught me like more than anyone else at uni. In one module, we had 3 projects, and the middle one, I'd say, changed my life. And it was just, it had such a big impact on me as a game developer. No one thought that, it wasn't built for game development, but it happened to be the perfect game development course. And I wrote a report. That was my homework. So what we're going to do is, this lecture, we're going to read my report from when I was your age, and we're using me at your age as our lecturer today. So we're just going to look back at what I did back then. So what I did was the numerical integration of differential equations, the damped harmonic oscillator by Alex Rose. My magic code, School of Physics and Astronomy, University of Manchester, Computer Techniques and Physics, April 2012. So it's coming on to a decade now. I'm an old man. Right. In the following project, and we are going to redo this project, but in Unity, a spring mass harmonic oscillator will be numerically simulated using various methods with the help of MATLAB. And in this case, not MATLAB, but Unity. Right, so the system, simulated, Alex, come on. This is not a good report, by the way, but don't worry, we're going to use notes too. The system consists of a 1.7 kilogram mass attached to a spring with a spring constant 1.7 Newton per meter. Isn't that convenient that they both happen to be 1.7? Let me grab the other zoom. Okay, there we go. So what it's going to be is, it's a spring with a mass. The mass is 1.7 kilograms, and the K is 1.7 kilogram, 1.7 M per M. And so this one has a force on it of Kx, right? If we stretch it. So F is minus Kx. So MA is minus Kx. So 1.7A is minus 1.7x. So A is minus x, right? So the acceleration is negative the distance at every point, right? If in a perfectly elastic system, okay? However, it has an arbitrary damping factor, B, which can be considered some sort of frictional force, and it starts from its rest position with velocity v, right? So here we can say that it's sitting on some surface and there's some kind of friction there, and so, it's got some BV back here, as well as Kx. So minus Kx minus BV, if that's forward, right? And then it's got some velocity v initially. Okay. So come on, Alex, there's bad science there. Or bad report. So, to begin, an analytical solution was found. This is such a bad report. It's because my lecture was so chill that I just wrote this like just a chill report. I didn't write it like it was scientific at all. Since this is a harmonic oscillator, it has the generic trial solution. Wait, what? What did I just do? Oh, that's interesting. It has the generic trial solution. X equals x to the minus gamma t over 2. Right, so let's write that down. So x equals e to the minus gamma 2 a cos omega t plus b sine omega t. Right? So if you look at this, this e function, as I'm sure I've drilled into your heads by now, starts as 1, because e to the 0 is 1, and goes down like this. So that becomes an envelope. Any a cos plus sine, as long as they have the same omega, they're going to add up to some sort of coherent wave, right? So you're going to end up with, you know, if it were purely cos, it would start here, right? But if it were purely sine, you know, if b was 0. If a is 0 and it's just sine, then it's going to look like that. But if it's some mix of the two, then it's going to look like, you know, maybe it starts there, right? And that's why you got these. Okay, so we got some function that looks like this. It wiggles, and then... Now, in this case, we're starting from the top, right? So, in this case, it's going to look like this. Right? Depending on what this gamma is, and depending what these omegas are, and, well, this can die. Okay, let's not unscribble it, then. Okay, so... where x is the displacement, gamma is b over m, where b is the damping factor, m is the mass, t is the time. We know that at t is 0, x is its initial x 0. So we can deduce this. Well, let's deduce it, because I'm not going to assume you can deduce it. Let's actually just deduce it ourselves. So we're looking at the beginning. When t is 0, we can see that x equals e to the 0, right, times a cos 0 plus b sine 0. Well, e to the 0 is 1. A cos 0 is a. B sine 0 is 0. So we can say that x equals a, right? X 0. X at the beginning is just a. Or more importantly, a is x 0. So this amplitude is the original x position, which is what we'd expect, right? If you've got a spring, the maximum amplitude of it is going to be where you start the spring from. It's not going to bounce further than you pulled it back, right? Then we can differentiate the original equation. Do we want to do this? I can do it if you want me to. If you can take my word for it, or we can. It's not that hard. Okay, we'll just do that really quick, just to prove that it's true. But I wouldn't expect you. You know, you're never going to have to do this. It's just for the sake of maths. So we have x equals a cos omega t e to the minus gamma t over 2 plus e to the minus gamma t 2 over t b sine omega t. Right? When you differentiate this, right, by dt, so we're going to dot it. I don't know if you remember differentiation by parts, hopefully you do, but all it means is you differentiate that first and times it by that, and then differentiate that and times it by that. So I'll show you what I mean. Let's differentiate this. This is really easy to differentiate e, right? You just grab the thing and bring it down. There we go, done. Times a cos omega t. And now we'll differentiate this side. So we leave this side alone, right? And differentiate this. So that's going to turn into a minus. We should really use an eraser for that. Or I should actually just predict the future and not do that. Right, minus, and then sine, you know, differentiate cos, you get minus sine. Okay, now let's do it on the right side. So again, minus, this is the exact same thing as that. Minus gamma over 2, e, blah, 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 b sine omega t. And now, you know, we differentiated that, left that alone. Now we're going to differentiate that, leave that alone. So, you know, we'll, wait, it's going to be negative again, as always. E to minus gamma over... Oh, no, it's not. It's actually not going to be negative, for once. We've got plus e to minus gamma t over 2 times differentiate sine, you get cos. So b sine omega t there. Sorry, that's cos. Well, actually, Alex, use your damn eraser, Alex. You have it for a reason. Okay, so you end up with this. Let's yank everything out of it. You got that. You know, Oh, actually, all of it, you can see every single one has this e. Right, so we'll yank the e out. E to the minus gamma 2 over 2 times y. And then half of them have this chunk underneath it. So we'll go gamma over 2. This, this part, a cos omega t minus. Oh, we'll put the minus in front because almost all of them are minus. So minus a cos omega t plus, because minus there. These are all minus, so it's plus. B sine omega t. Okay, and then the rest of these are just alone, right? So plus a sine omega t minus b cos omega t. Right, so we get this formula, that's v. Right. Memorize it really quick. See, oh, look, it's the same thing. Oh, wait, no, it's not the same thing. I messed up. When I differentiated them. Because when you differentiate sine omega t, you get omega sine omega t, right? So that has an omega there, that has an omega there, that has an omega, that has an omega. Okay. So just in case you wanted to know, that's why that is. But if you plug t as 0 into here, alright, we'll just do it. We'll just get through it. We're plugging t as 0, so we get minus e to the 0 times that times a cos 0 is 0, so a. Sine disappears, right? Plus a, alright, this time that disappears, so we've got minus minus, okay, omega b. Right, so that disappears, and we end up with v equals. Oh, I didn't have it open. Well, I subbed in 0. Okay, and you can just do it yourself, right? These are gonna disappear, the signs are gonna disappear, the e's gonna disappear. You'll just be left with this. I promise you. It doesn't really matter, right? This is just the formula. But the point is, we end up with the analytical solution, which you've already seen before. If we go into Unity, right? The analytical solution is this. It's the one that just uses maths to generate the results. So every point, it uses the formula, and we have a spring. Okay, this time we got a vertical spring, but it could be any spring. Right. So, sorry that I just didn't do that on screen, but whatever. The acceleration term is taken from the two forces, Fx, Kx and Bv. By plotting the kinetic energy and the potential energy and the total energy on the same graph, we can see that energy is conserved. Because look, we start off with the blue one's kinetic, right? The black is these added together. So this top line is the total energy. You see it never changes. It's always the peak value. And then, these go from 0 to max. This is what the energy graph should look like. Right. However, we don't always want to do this, right? This method is extremely accurate. But if we add an arbitrary force to this equation, right? So if we were to say, well, what if we add gravity to the equation randomly, like at just some point, or we just shove it, and we want to solve it analytically, it becomes increasingly difficult and requires complicated Fourier analysis, which we definitely are not doing. No. So there are a number of numerical methods of integration we can use to simulate this system. The first method is called the Euler method. Ding, ding, ding. You might be alarm bells ringing because this is on the syllabus, right? And we've mentioned it before. This is a very simple method which works in 3 steps. You take the acceleration at the time. So in Unity, we set the acceleration ourselves all the time, right, using force. And then the velocity, v at, v at the current time plus some delta time is found by adding the delta time multiplied by the acceleration to v. Of course, an infinitesimally small value cannot be achieved, so we use a small time step. So in this report, I use the word h. When you see the word h, think time dot fixed delta time. H is just the fixed delta time. So finally then the displacement is found by adding h times v to x, right? And then this happens, right? So what I've done in Unity is I made a new one. Do you remember, this is different from last lesson. We had one called damped harmonic oscillator and we had the analytical one, right? So the damped one used rigid bodies. This one uses like maths. But now I've made my own rigid body called Euler body, right? So this new oscillator is the same as the old one, except instead of here we used to use rigid body, now we use, instead of using rigid body, we use Euler body now. So this Euler body, right, all it does is, it has all the functions of a rigid body. You know, it has add force, which you see as A is F over M, set position, which sets the internal position and or past registers. This just means the position -1, the position -2. And then on fixed update, it does an Euler integration, or it can do an improved Euler, Euler-Cromer. There's many ways of doing it, but we're talking about Euler right now. Okay, and then it sets this position to the position it's calculated using this method. So this is the Euler. So what we do is S, the position, plus equals V times dt, where dt is just fixed all the time, right? And V plus equals A dt. So let's see what happens. We're going to run the Euler method, and we're going to run this one side by side with it, and watch. Oh no, that's not a very good method, is it? Because this one is going crazy, right? It's just accelerating to infinity. And if you look, here's what the graph looks like. You know, this method is very flawed. As oscillations occur, the maximum displacement increases with time. This causes the total energy to increase. After merely 50 seconds, the energy is increased by an order of over a magnitude of over 100. Clearly, this is unsatisfactory. Now, the reason for this is a couple of things. Well, the main one is that, you know, you're turning. I've talked about this many, many times. You've seen me draw this same thing over and over again. But if you're trying to integrate these parallelograms, right, and your parallelograms are too big, then your smooth curve, you're cutting pieces out of it here. You know, these pieces are left over. But even if you were to make it really, really thin and make your slices super ridiculously thin, right, you'd still get this problem because, let's see an example. Let's open up Excel, right? I'm going to give you a riddle. First one to get the right answer gets a gold star. Okay, what is the answer to this equation? Ready? You ready? Everyone ready? Ready? This is quiz time. 0.5 minus 0.4 minus 0.1. What's the solution? Someone tell me. Is 0. Is that what you think? It's actually 2.77556 e to the minus 17. Yeah. Yeah, exactly. So, you know, here's the thing. Computers can't do maths, right? Another example is, let's say that was Excel, right? Unity would never make such a problem. Well, let's see. Print 0.5 minus 0.4 minus 0.1. What could go wrong, right? Let's run this. Let's check the console. Oh, minus 7.458 e to the minus 9. Right, so Unity can't do basic maths, right? The game engine you're working in can't do the most simple sums that I'm sure I could give this to many primary school children and they would be able to answer this question correctly. But Unity can't, because, you know, you'll notice that these numbers are different as well. This one was e to the minus 9, and this one was e to the minus 17. The reason being is one uses a floating point number and one uses a double floating point. So, you know, one is accurate, to a float is accurate to 1, 2, 3, 4, 5, 6, 7, 8, right? And a double is accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't know where the 1 is. Maybe it's somewhere around there, right? It's something like this, right? And that's the problem, right? Eventually it will do the sum correctly, but it will finally get to the final point and be like, oh, well, there's this 1 left over. And so even if you made the perfect simulation right, there's always going to be this little bit of chunk left over. And it doesn't matter how small your time step is, you're going to lose energy over time. Okay? So this Euler method is flawed, and that's a problem, because how are you going to do game development if you can't even track where anything is, right? Well, an improvement can be made to this method. So we create a new method called the improved Euler method. The way this method differs from the Euler method is that the displacement term takes into account an additional acceleration term as followed. So x equals x plus hv times h squared at. Remember, h is delta t. I'll write this down in easier language, right? So we'll write down our Euler method. So our Euler method was x n plus 1 equals xn plus vn times dt, and vn plus 1 equals vn plus an dt. You can do these any way round, it doesn't really matter, right? Well, we do it this way around because then we're not going to get a problem. But like, I shouldn't have said that actually. You do it this way around. But if we're in MATLAB, you know, we were creating a big array. So instead of using, in MATLAB, when I wrote this report, I was making a big graph of all the values. I had x1, x2, x3. Whereas in Unity, we don't store all the past, you know, we just store the current value. So, this improved Euler method instead does this. Xn plus 1 equals xn plus vn dt plus half an dt squared. Okay? And then the v is the same, you know, vm plus 1 equals vm plus an dt. Right? So if we will touch on Suvat equations, but if you've done them before, you may recognize this formula as S equals ut plus half at squared, right? Which is a standard equation of linear motion, right? So yeah, the improved Euler method, let's have a look at it. We implemented it here, we got Euler. This time, you know, we done the same thing, but we added half at squared to it. All right. So let's, what is that going on about? All right, let's enable this. So now we have a red one and a blue one. Okay. So the blue one is the Euler method, and the red one is the improved Euler method. And let's watch them on top of each other. Right. Well, you can see that the red one's doing better, very clearly, right? It's still not great, but it's better. It is an improved method. All right. So let's go back to the report. So you see, this time, the energy graph isn't just going up normally, it's actually wibbling up. It's like a sine wave. In fact, if I had to take a stab at what that graph is going to be, you know, it's going to be some e, right? Because it's going up. So it's going to be e to the, you know, lambda t times by, and if you see, it starts in the middle, so it's a sine wave and goes up. So this energy is something like sine some omega t times the initial energy, right? That's going to be the energy here. Right, so some e, so it goes whoop, bounded to a sine wave. Okay. Actually not quite, because it's got its initial value too. I'm lying. Plus some k, plus e naught, or maybe it's not that at all. Who cares? But, you can see that it's wiggling up. What did I say? From this graph, we can deduce two pieces of information. First, this method is evidently more practical than Euler. Secondly, the total energy is fluctuating sinusoidally. This is because the method bases subsequent displacements on previous velocities and so blah, 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 blah. It doesn't really matter, does it? Because we're not going to use that. But one thing that happened in the when I was doing this experiment was I accidentally discovered the Euler-Cromer method, which we were not asked to do. We were actually asked to do the improved Euler, and the Verlet method. But at some point I realized this other method, the Euler-Cromer method, and I just said to my lecturer, like, mine's stable. And he was like, oh yeah, that's not the Euler method, that's the Euler-Cromer method. All right, so I wrote through this in. There's a better way of improving the Euler method, namely the Euler-Cromer method. By making the tiny change of adding the current velocity onto the displacement rather than the previous velocity, the accuracy of the system increases phenomenally. All right, so what that means is Euler-Cromer, instead of this, we do Vn plus 1 is Vn plus an dt. Then we do x n plus 1 equals xn plus Vn plus 1, this is different, dt. And that makes all the difference. So if you see in unity, Euler-Cromer, V is there, S is there, right? We just switched them round. Well, now watch what happens. Euler-Cromer. And that's the improved Euler there. You see, it works. It works quite well. Now, would you like to take a guess which one of these systems Unity uses? Now, I actually can't say for sure that Unity does use the Euler-Cromer method, but I'm pretty sure they use the Euler-Cromer method, right? Because look, it's stable, it works. I mean, it's one frame behind, but it's working, right? This is what you expect to see. Right? Looks good to me. So, what has it got in its pockets is, if we look, yeah, you see that basically these get stomped by Verlet. This is the Verlet method. The Verlet method is another way of doing stuff, but the problem with the Verlet method is it's only for like a mass on a spring. It also simulates, but it's much more complicated. And you also can't. I mean, you can change values, but you may as well be using an analytical solution at this point. But you can see that the Verlet method is actually more stable, but it's only good for a very specific scenario. The Euler-Cromer does actually change energy. The energy changes by a really small amount. I made it look big in this graph, but it really isn't. But the Verlet is just really small. Although the Verlet energy creates energy, you see the average energy is greater than it should be. But the Euler-Cromer method, the energy is in the right place. We can deduce the Euler-Cromer method is significantly more inconsistent than Verlet. Disagree, but oscillates around the true value. A clear way of comparing the 5 methods is by plotting displacement against velocity. And if no energy is created, it should be a circle, otherwise it will spiral out of control. So if you see here, these are spiraling out of control. These ones, I don't know why I used black for 2 different, that's stupid, isn't it? But whatever, you can see that these, they're good. They don't spiral. Okay. I just want to quickly show you something interesting, to me at least. So this is, this was when you Google improved Euler, it's actually called Hyun's method, maybe. I don't know if that's how it's pronounced. I don't know what nationality it is. Maybe Korean? I don't know. No, I have no idea. Maybe it's German or something. So this method is, it doesn't matter because it's rubbish. Let's not use it. But if you Google Euler-Cromer, you end up with this, the semi-implicit Euler method. Right? It's got many names. Euler-Cromer, Newton-Stormer, Verlet, right? So if you look here, it's stable at these regions. Now, this graph may look weird or scary to you. It's an imaginary versus real graph. The reason being, if you remembered that, this is a differential equation, and so this equation, we talked about how it has some solution that's like this, right? Equals, I forget what it was equal to, but so you're going to end up with minus b plus or minus root b squared minus 4ac all over 2a, right? So it's possible for this, if 4ac is too big, it can create an imaginary value, or it can create a real value. But you can see here that even if it's imaginary, it can still be stable at small numbers. It just depends like how big the values are compared to each other. So what I'll show you is we'll put on a damping factor of a gamma of 100, and we'll show that it's not stable anymore. Do you see this is going mad? It's just wiggling, like, right? And actually, it's going past the point now. It's gone past the point it should have stopped at, and it's just like teleporting, right? Whereas the analytical solution's just fine. So you can see that even the method Unity uses isn't perfectly accurate. You can have big problems. We've seen that in the past. We've seen a few problems like the friction thing. We've seen this problem several times in the course. Maybe you noticed it. But either way, it's stable. It's stable for small time steps in general. So at non-giant velocities. So generally it conserves energy, and it's a pretty good method. How much time we got left? Oh, we got time. Right, one thing I just want to show you is I also went into damping here, so we can see examples of some graphs. Like this is, the red one's critical damping. I mean black. So you can see here that this we shoot off a spring, and then it settles at the right value at the minimal time. If you use half damp, then it will overshoot and wiggle back. If you over damp, then it will, it will take too long to get back to where it was. Right, and we can see that at 10 seconds, we can add 10 newtons, an arbitrary force. We can just add some newtons, and then it will wiggle and wobble to the right value, right? But if we don't have any drag, it will do this. It will wobble up, and then it will start wobbling around the new value. And depending where it was when you pushed it, you'll get a different graph. So if you see here, this one has a smaller amplitude than when it started. But now, we push it here, now it has like the same amplitude, right? Or if we push it when it's at a minimum, then now it has double amplitude. So this time we started pushing it, we changed where it's going at 11 seconds, and now, it's wobbling double. So, yeah, that's that. Right. So, what's the point of this? When can I use it, Alex? You talk about how this changed everything for you, but why is this so important? Okay, let's talk about my favorite function in the history of mathematics, the lerp, linear interpolation. Okay, Unity has its own written lerp, but it's more fun if we write our own lerp, right? So, the lerp says that you take your x, right, your xn plus 1, and you add, you take your xn, and you add your desired position, the place you're lerping to, minus xn, times some lerp factor. You've seen this before when we talked about drag, because I said, oh, well, drag, you can just do this. Well, that's the same as lerping to 0. Or we actually, remember we talked about if you do moving platforms, you could lerp to the platform's velocity instead. In fact, I actually said that. I said you should lerp to it, and I didn't really explain lerps. Well, now we're explaining lerps, right? This is a lerp to 0. The reason being, it follows this formula, right? If we do n plus 1 equals xn plus 0 minus xn times by 0.1f, right? You can see this is the same as xn plus 1, and then equals xn, xn 1 minus 0.1, right? Which is the same as 0.9. So this thing is just a lerp to 0, right? It's the same thing. It's the same as this. Right? Wait, what? Oh, sorry, yeah, it's the same as this. We just, our desired was 0. So we lerp to 0. But you can lerp to any value. So let's, just in case this isn't clear, let's just write a lerp. Right. We're gonna write a lerp. Live coding. We'll call it lerp 3 because I practiced this twice. Okay. Right, so lerp 3. We're gonna add, why did I do that? We're gonna rigid body dot velocity r. In start, we're gonna say r is equal to, that. And then we're gonna have some, lerp target. We'll call it target, right? And then in fixed update, not update, we'll say, that's really annoying me, that line, let's get rid of that. We'll say that the transform.position plus equals the target minus the current position times the lerp factor. Right? Oh no, we actually make it. We should make it public. Right? So it's that simple. Let's see what happens. Oh, also, let's make the target the current position. So it will always lerp home now. The target's where it started. Right, so let's drag in a thing. Put the lerp 3 on it. Right, run it. Right, let's move it away, and now put some value on it. Oh, it's lerping. It's lerping. So 0.1 means it lerps 10% of the way every single frame. So every frame it's going 10% closer to its original position. Now let's say we want it at 1. That means it will always, it's instant. We drag it away, it will instantly snap back. Okay? Let's say we have it at 0.03, then now it's slow. Right? Smooth pans. When might you ever want this in game development? A smooth pan. Well, let's say, okay, let's make it lerp to a target instead, right? Say instead of a position, we're going to change this to a public transform. Right, so now it's going to go to a target. And let's, what? Right, so now what we'll do is we'll stick the lerp 3 on the camera, set its target to this thing, and then put the lerp at 3%. And look at that, now we have a camera that pans towards the target. Ooh, magic. Something you might want all the time. So one other good thing about this, well, okay, one thing you should be aware of as well, you've got to be careful of this, is you see the camera isn't actually looking at this right now. That's because in 3D, it's actually panned into the z-axis. If I slide this out now, it appears again, but then the camera's going to pan towards it, and it's going to get so close that it clips out, right? So you should always make sure if you lerp your camera, you don't lerp it z, or you make sure it lerps, ignoring the z. But, okay, we've got lerps, but what if we want to lerp? Lerping's quite cool and useful, but what if we want to lerp by velocity? Well, if we've seen that the lerp x n plus 1 equals x n plus the final position minus the current position times your lerp factor, right, where 1 is 100% lerp, it will instantly snap to the right position, 0 is nothing. Don't try 2, it's a bad idea, right? If you've got x is this, right, then we also know from the Euler-Cromer method that xn plus 1 equals xn plus vn plus 1 dt. So if we want to just find out how to, okay, here's the problem. if we have a rigid body and we change its transformed opposition, right? If you ever take a rigid body, right, and you set the transformed position, it will not do collision detection properly because you're setting the position, right? That's not using the rigid body. When you use a rigid body, you want to set all motion using the rigid body. So you can use r.move position. That will move it directly. But there's a problem with move position is that you can teleport through walls and stuff like that. If we don't want to teleport through walls, if you just want it to still retain collision detection but have a lerp, then we'll want to use the method I'm using now, which is we look at what the position would be if we weren't to use rigid bodies, and then we just grab the velocity. So, in this case, let's get rid of this. These are equal to each other. Well, you can see that these two cancel. So if we want v, we just put the dt here, and that's it. V is xd minus xnk over dt. So let's do that. Instead of using this, we're now going to use a rigid body. R.velocity equals target.position minus transform.position times lerp factor divided by time.fixed delta time. Get rid of that. Actually put a semicolon at the end of the line. No, the end of the line. Stupid thing. I believe that's right. So we're going to stick a rigid body on it this time. We want no drag, no gravity. Right. Put the lerp back on. We'll make a new anchor for it. Right. So we'll make this red. Put it higher in the sprite layer so we can always see it. Remove the scale. Set that to the lerp target. So now the white thing will lerp to the red thing. Okay. And now give it that actual number. Right, so now we're doing the same thing, but it's using velocity. The reason that's useful is, let's say we add a box collider to this, right? Whereas before, nothing would have happened. Now if we add, we put a box in the way, add a box collider to this, just make this like blue so you can actually see, right? Then now it's lerping, but, it's not going to teleport to it, right? It's going to get stuck on the wall. That's cool. Isn't physics cool? God, I love physics. So cool. Right, look at that. Oh, it's cool. Right, anyway. So, we could add some angular drag to this so it'll be less crazy. Oh, I love physics. Isn't it just amazing? Right. So anyway. So we have this. But let's just think about something a sec, right? Oh, this is so cool. Well, you might want to do something like this, You might want, if you're making a game where you've got like a ship, like a, you're doing like a shooter and you want the ship to follow the mouse so you can shoot at things, then, you do it like this. But what if for a minute we said, let's do something crazy. Let's add that, okay? Okay, sorry, I need to cast the vectors here, because otherwise it's going to complain. We're going to add it on. So this time, instead of telling it to go to the value, remember that a spring is always moving towards a point, right? So what we've done here, by adding, we're creating a harmonic oscillator. We're not just telling it to lerp to the point, we're telling it to oscillate around the lerp point as like a spring, right? Just see what I mean. You'll see. Let's give it some value. Look. Now when we drag it around, we can, I can make it do this, watch. I can make it orbit. Right? Now if we add some drag to it, then we get damping in our harmonic oscillator. What happens when we damp our harmonic oscillator? Well, that happens, right? So now we can, or I can do a small thing like that, or I can make it orbit large, like that. I can make a large orbit by going out of, as long as I keep like 90 degrees out of phase with it, then I'll make the orbit get larger. If I go with a larger amplitude, you say, right? So, you know, and that's just one line of code. It's one line of code. Isn't that cool? It's one line of code, right? And it's a really simple line of code. And we got all this behavior from it, right? And there's so much we can do with this. Say this is a part of your menu. You might just want a menu that has a wiggle to it, right? So let's just give more drag, right? And now what happens? Right, well, maybe that's not enough drag for a menu. So let's put it more like that, right? So now, you know, the menu flops down. Zoom, zoom, zoom. It doesn't come straight down. It smooths in. But, okay, that's nice. Well, if we have it 50, that's like supercritical damping, right? Now it's just going to pan slowly like a camera. But what if we instead make it go really like 15 or something, right? Now we're going to get a little wibble wobble. You know, sometimes you want that. You just want a little wibble wobble. Like, imagine there's like you've got a game and you've got the hero, and the hero has like a little, like, you know, like a bird that follows you around, or like a, you know, a fairy or something, like a man. Then you can just make it lerp towards you, and it still has collisions, right? If we spawn this thing, right? We've got 2 of them now. Stick a box collider on this one. Stick a box collider on this one. All right. Then now, you know, I don't understand why. Oh, did I put the box collider on the wrong thing? Yeah, I accidentally put it on this. Right, so now they're wibble wobbling off each other with physics, right? And we can change how much. Maybe this one critically damps and this one doesn't. You know, there's just so much behavior you can get. Or let's say, you know, there's all kind of, okay, we'll get into it. I was about to spoil and I was like, wait, I can do that in another lecture. But you see here that it's just such a powerful tool. It's amazing. It's so good, and all it is Euler-Cromer. This thing already does the Euler-Cromer method itself. I mean, we can do the same thing using my rigid body here. We could write the same function, you know, instead of giving it this, we could use this Euler body. But the point is, like, I don't know what the point is. The point is it's cool. There's no point. It's just physics. I've taught you it now. I hope you remember it, right? So, you know, this is your magic formula that you can use to do all your stuff. And if you do it like this, Vn plus 1 equals Vn plus this thing. Now we got a spring going, right? Because that's essentially Kx, right? Right? Over dt. But I mean, it's V, so, you know, V is dx by dt, so we've got the dt in there. Alright? So we're basically adding a spring instead of a lerp. It's like a lerp, but it's a spring. Oh, it's so amazing that lerp and spring, they're so close to each other. They're just 1 equals away. They're just 1 initial position away from a lerp being a spring. Isn't that so cool? I've never really thought about that. That's amazing. This universe we're in, it's just the universe that keeps on giving. Yeah, and then, yeah, is there anything else profound that's going to drop out of this formula? Kx. Oh, and then we do the drag, right? And then, you know, then we added a drag, which was the minus bv, which here we just do the minus b, because it's already a v. Yeah, like, okay, I'm done getting really excited about physics. Any questions? Do you see you have this fairy and it follows you around? Right, that's using all of this. It's also using a sine wave on top of that. This guy as well, this guy is doing the exact same thing. And the 5 little balls he's got, they're just using, you know, trigonometry and that stuff. You know, so you see like the balls, it doesn't really matter that there's stuff in the way, they're still like finding their ways around things. I mean, if I just click to random timestamps in the game, you're gonna find like these guys, these hammers, they're doing the same thing. Those guys are using, those fire dudes were using trigonometry as well. They're just using the sine wave to go left and right. This guy, his feet are going, you know, it's lerping here, and then once it's at a reasonable value, it does a stomp. And then, like, his head is lerping, and, like, yeah, so, I mean, it's really up to you how you use it. Like, there's all kinds of things you can do.